Alrighty, hello. Today we got a pretty simple word problem. Simple as in like it's just one sentence. It says, at what speed does a clock move if it is measured to run at a rate 1/2 the rate of a clock at rest with respect to an observer? So I know that sounds kind of crazy. It is a crazy sentence, but let's just outline what is important. So we have a clock, right? This is a clock. It is moving. Let's put it in a specific reference frame. Maybe it's on a spaceship or something, but it's moving with some velocity v, right? And we want to find this velocity. If we find this velocity, we answer the question. They give us some information, which I'm going to read again here. It says, at what speed does a clock move if it is measured to run at a rate 1/2 the rate of a clock at rest with respect to an observer? So let's say here we are on Earth, right? This is us on Earth, and we have a tiny clock here too. Clock rest. Clock at rest. All right, so this clock is moving, right? We could see it from here. We are at rest. We could see this clock. This clock is at rest with respect to us. We are in the Earth reference frame. And we can see another clock here in this moving reference frame. It's moving past us here. So because of one of the consequences of special relativity, time dilation, we know that this clock is ticking at a different rate than this clock. Pretty crazy. And they tell us that the ticking is exactly 1/2. So the clock that is moving runs at a rate 1/2 the rate of a clock at rest with respect to the observer. So let me write that piece of information in blue. Rate equals 1/2 of clock at rest. I just write it like this. The rate of this clock is 1/2 multiplied by the rate of the clock at rest. So I'm just piecing together kind of the word problem here. But I would like to use an equation here that can help us, because I don't really know what to do here. Like we're looking for velocity. We have 1/2. Like there's no numbers in this problem. So I'm just trying to draw some kind of comparisons here. And I'm trying to draw some numbers. And I want to find an equation that I can use. Now, since we're talking about time, I know that here we could use the time dilation equation. I'm almost positive of this. I'm going to peep earlier in the chapter where we are introduced to time dilation, where you could just look at the section. Actually, let me check section consequences of special theory of relativity, 39.4, simultaneity of relativity. Okay, here we go. Time dilation equation. So the time dilation equation looks pretty crazy. I'm actually gonna write it here in green. Delta t is equal to, we get a fraction here, delta t subscript p. We got square root 1 minus v squared c squared, boom. And they also tell you this whole thing is equal to gamma delta t subscript p. Okay, now I feel a little comfortable. I can kind of feel like we're on the right path here. The reason I feel like we're on the right path is because they don't give us any numbers, but they do give us a ratio. So the rate of this clock and the rate of this clock, if I divide this over, I get this rate of clock 1, let's say, and let's say this is clock 2. Rate of clock 1 divided by rate of clock 2. All right, I'm just taking this, boom, dividing it here. We get that this is 1/2, right? The division of the rates at which the clocks are ticking, right? One clock is ticking faster than the other. We could figure out that this is the factor by which, I mean, the problem actually tells us this. I'm just trying to word it to myself in a different way. Now, why is this important? Because take a look at this. We have one time over here. Maybe we can say this is one of the rates, rate A, let's say. I don't want to say rate 1 or 2 because I don't want to confuse it between these. And then we have another one over here. I can call this rate B. And the second I started feeling a bit comfortable is because here we have three things. We have one thing here, one thing here, and one thing here. If we do some cross multiplication, I can move this whole thing here and get a ratio between these two rates, which is exactly the ratio I'm getting here with these two rates. So let's manipulate this equation. I'm basically going to multiply this on both sides, divide this on both sides, and I get square root 1 minus v squared c squared is equal to, then we have delta t subscript p. We're going to talk about what this p means. This is going to be helpful to solve the problem. But right now I'm just working with the equation. And then we have the delta t, which is the one that we had here. So this now gives us a rate fraction. It's kind of the same as this fraction here. So take a look at this. If I put this here, and I don't know if the rates are like this or if they're flipped. So in here, we have two options. Either the rate is 1/2 or either the rate is 2, right? So either we plug the numbers in exactly like this. We have one rate here, one rate here, one rate here, one rate here, and it's 1/2. Or we flip them because here we have t subscript p. I don't know which one the p is. We're going to talk about that in a sec. So either it's like this or it's flipped, and we have literally two options. Either it's 1/2 or 2 on this side of the equality. Now, since we have something on this side of the equality, and we have this side of the equality, we know what 1 is, we know what c squared is, and we're looking for v. Now we could just do some algebra, solve for it, and we get the answer here. You see how I'm trying to work this out? So this is my strategy. There might be another strategy in the book. I actually have the solution for this because I think it's an odd numbered problem. This, I believe, is problem number 7. Problem 7, chapter 39. We're going to take a look at that in a second. It might not be problem 7, I may have forgotten. But anyway, this is my strategy. And how I'm going to figure out if it's 1/2 or 2 is I remember that this t subscript p is the proper time. What does the proper time mean? It is the time, how can I explain this without confusing myself or confusing the Spidey Physics viewers? Proper time and proper length is if you're chilling, wait, can you guys even see this? Maybe you can't. If we're chilling in a specific reference frame, and I have a clock over here, I know that this is the proper time. And if I have a meter stick over here, this is related to length contraction problems, I know that this is the proper length. It's called proper because I, the observer, am in the same reference frame as the object I'm measuring, right? We're both in this reference frame. So I know that there's no relativistic effects happening to the time or to the length of these objects because I'm in the same frame of reference with them. They're not moving anywhere. So there's no relativistic effects. Remember, relativistic effects happen when you have a velocity very close to the speed of light. In this case, we have this clock here, which is moving past us. So my argument is, and we're going to figure out if it's a correct argument when we see if the answer is right or not, that the proper time is this one over here, the clock which is at rest with respect to my reference frame. The delta t, which is this one here, the one without a p over here, remember the original equation has a delta t subscript p, the proper time, and here you can call this the time dilation time. The time dilated time. So this is the time that stretches or squishes based on relativistic effects. So now that we know that, I know that I can put rate of clock 1, which is this 1, I can put that over here, which is on the bottom. And then rate of clock 2, which is this 2 over here, I can put it at the top. So what that says is this 1/2 is not the correct thing, and we actually have 2 over here. Is that true? I don't know if it's true. You know what? We're gonna solve the answer because I'm just making a guess here. We're gonna move through with it. At the end of the day, I know one thing, which is nothing can go faster than the speed of light. So if I get this velocity equals 2 times the speed of light, 3 times, 5 times the speed of light, I know something went wrong. But if I still feel uncomfortable and I don't get something that's going 2 times the speed of light, I can just solve the problem with both of these and then see what happens. Maybe I can do some reverse engineering to solve the problem. So I hope that is a good strategy for you guys. A lot of rambling here, but basically I'm gonna erase this here. I'm gonna erase this. I'm gonna erase this whole circle here, and then erase this too. Actually, I'll erase this and then do the entire calculation in black over here. So we have square root 1 minus v squared c squared. I said this is equal to 2, which is the ratio between the time dilated time, or sorry, the proper time, which is what we're saying is 1, and the time dilated time, which we're saying is 1/2. 1 over 1/2 equals 2. So anyway, I'm kind of just thinking if this is the proper solution. What we have here is square root, so I'm going to square both sides. If I square both sides, this square root gets removed. I get 2 to the power of 2, which is 4. Now I can move some stuff around. I'm going to add this to this side. I'm going to subtract this to this side. 1 minus 4. Okay, we're at a problem here. 1 minus 4 is a negative number, which I don't think looks good. All right, we have this. 1 minus 4, negative 3. Oh, man. We're screwed. We are screwed because look at this. I want to isolate for v squared, right? I have v squared over c squared here. Multiply c squared, and in this side I have negative 3c squared equals v squared. Square root this, square root this. Square root of a negative number is an imaginary number, and we cannot have velocities that are imaginary. So automatically, I've gone down this path, and I see that something is wrong. So what I think is wrong is I made a mistake at this stage when I chose the rate to be 2. I think the rate should be 1/2 here. So my confusion here is, I don't know, a bit weird. I haven't used this equation before, so I'm just making a mistake here. But it's okay. Let's check this one here, and maybe even this is incorrect and I made another mistake earlier on. We're going to see. But right now, we can move on like this. Square this, square both sides. Square this. What I have is 1 minus v squared c squared. 1 squared is 1. 2 squared is like that. So now I think we are fairly solid. I'll subtract this on this side. Minus 1 over 4 equals, add this on this side, v squared over c squared. 1 minus a quarter is 0.75. Right, this is 1, this is 0.25. 1 minus 0.25 is 0.75. This looks okay to me, right? This looks okay because we have this. Now I can move up here. Hopefully you guys can see this. Multiply this c on this side, and then I get an equation for v squared is equal to 0.75 c squared. Square root both sides. The square root here cancels this 2, this 2 exponent. The square root here cancels this, but we have a square root 0.75. So we have final velocity is equal to square root 0.75. Outside the square root, we have c. So this is a percentage of the speed of light. What is square root 0.75? I'm not sure. Let me check my calculator here. I have square root 0.75 close bracket equals 0.866. The velocity of the clock here is 86.6% the speed of light. The speed of light is not broken, which is good. And what we're saying is if all of the theory here looks good, this clock must be moving 86, 87% the speed of light for the tick marks on this clock to be half the speed of the tick marks over here. This is like that one scene in Interstellar when Cooper, Matthew McConaughey goes to the planet near Gargantua, and they're saying like 1 hour on this planet is 7 years on Earth. If you haven't seen that movie, check it out. It's really cool. Basically, this is what's happening there. But I'm not sure if that's the right answer because I did some kind of meddling around with the ratio over here. But at the end of the day, this is the equation that we're looking at. If we feel uncomfortable with this, we now have the velocity of the clock. So we can use the time dilation equation and put length of time. Here I can put 1 second. This is the time that I measure on my clock on Earth. Then I can plug into here the velocity that we got of the clock over there. Here I should get some gamma factor, and then here I get some answer, and I should get the time dilated time, which means after 1 second of me measuring time here, how many seconds passes over here. And since the clock rate here we said was 1/2 the clock rate here we should get 0.5 seconds. I hope that makes sense. Anyway, you can do that on a test to reverse engineer, see if you find an answer. But in this case, I have the solution manual of the book, which I saw was, let me actually check what problem was this. Here it is. The speed is 0.66 times c. This is the correct answer. Thank you guys as always for watching. I will see you in the next video. Peace.